Okay. You might have seen a chart like this in 305 and maybe not. Intermolecular forces are centered around electronegativity values. The more electronegative something is, the more polar that atom is because it wants electrons. So okay, so electronegativity is a tendency of one atom to attract another electron cloud. So in this chart here, fluorine is the most electronegative, and they have some values placed on them. Linus Pauling did except for this one. I have about 3 of these charts, and all of them have electronegativity values on it, except this one. Let's see, most of these I already know. Let's see, fluorine is the fluorine is 4.0. Hydrogen is I'm going to do this differently here. We are going to whip over to okay, much better. Okay. So fluorine 4.0, and then bottom left, cesium and francium are 0.7. So basically, top right is the most electronegative, bottom left, least. Okay. And again, the definition of that is the tendency of one atom to attract another's electronic cloud. Now, this has to do with the electronic configurations you did in 305, you know, the 1s, 2s2, 2p6. Remember all those? When you're filling a subshell. And the more full the subshell is, the more stable it is. So that's why electrons on the top right want to fill those subshells as much as possible to gain stability. Okay, so intermolecular forces are directly related to electronegativity, as I was saying before. So this is the relationship. Let's say we're looking at the OH. I've already mentioned, we talked about alcohols, that alcohols are very, very polar, very high intermolecular forces. This will show you why. Okay, so we're going to look at the delta electronegativity, abbreviated. If it's greater than or equal to 0.5, this is considered a polar bond. If it's 2, it's considered an ionic bond. It's so incredibly polar. So let's look at what the values for OH are. Okay, oxygen is 3.5 and hydrogen is 2.1. So that's way above 0.5, way above 0.5. So the hydroxyl functional group is considered extremely polar. If we look at just a plain old oxygen, say oxygen to carbon, okay, oxygen is 3.5. Carbon is 2.5. So any oxygen atom contributes a lot of polarity. So here, an oxygen to carbon, for example, if we're looking at a ether, for example, you'd have these polar oxygen bonds in there. If we look at something very simple like carbon to hydrogen, okay, carbon is 2.5, hydrogen is 2.1, so we're ending up with a 0.4. So the carbon-hydrogen bond is not considered polar. Now, if you think about alkanes, what atoms are involved in alkanes? What two atoms? Carbon and hydrogen, period. Carbon and hydrogen have a 0.4. That's why alkanes are so nonpolar. Now, you can actually go all the way down to 0. For example, if we're looking at a carbon-carbon bond, but also in alkanes, that would be 0. So like atoms, like nitrogen to nitrogen, carbon to carbon, oxygen to oxygen, those have no polarity. So another way to talk about a polar bond is to say it's lopsided. One side of the bond is much more electronegative than the other side. That's the side of the bond that has the most electronegativity. If an atom is polar, it's said to possess a dipole. Okay, di meaning two, pole or polarity. The higher that difference in electronegativity, the stronger the dipole. It looks like that. This points to the positive and negative side of the bond. So in this situation up here, for example, it would look like that. Now there has to be some difference for a dipole to form. Now a dipole is a vector. And when you get into physics and more advanced chemistry, you start talking about forces, and forces have direction and they also have a quantity. Now, if they're going in the opposite directions, two dipoles can actually cancel each other out. If the direction is exactly opposite and the quantity is the same, they'll cancel each other out. Carbon dioxide is a good example of that. We have a dipole here and here. And those dipoles are exactly the same length and opposing direction. So they cancel each other out. Now, if you ever have to take a physics class, you're going to work with vectors a lot, especially in early physics. You're going to work with vectors a lot, and that's an understatement. You're going to be taking them apart in a trigonometric relationship and looking at each x, y, and z component of that vector. But in this class, all we're doing is saying pole exists and it's a vector. Okay, so I haven't talked about intermolecular forces yet. So if we have a molecule one thing I forgot to mention is this is a continuum going from 0 to 2. And scientists over the years have just put some mileposts down at 0.5 and 2. But if you're 0.48, quote unquote, it's nonpolar, but you're almost at 0.5. So the character as you go along this line becomes more and more polar. And then as soon as you hit 0.5, up, it's polar now. So if you've got two bonds, one here and one here, the one closer to the 0.5 is going to be more polar, even though it's considered nonpolar. It's got some polarity or polar character to it. All right. So frequently when I'm talking from this point on, I'm going to be talking about intermolecular forces and how the functional groups will affect that intermolecular force. So let's look at a of intermolecular force strength. Some people consider an ionic bond a non-shared bond because by definition, ionic bond means an electron or two has been totally transferred. But it is difference of electronegativity of two or more, it's considered ionic. So it's the strongest of the intermolecular forces. Okay. The next one down is hydrogen bonding. Next one down is dipole-dipole in decreasing weaknesses now. And lastly, we have something called London dispersion force, which is the weakest. So if you have a difference of 0.5 electronegativity, when you're looking at it, a molecule, bond-wise, polarity. So you have increased intermolecular forces there. If by chance you don't have anything above 0.5, you always have London dispersion forces. So all molecules, no exceptions, have London dispersion forces. So let me talk about that. And we can abbreviate that as LDF. Okay, if we have, let's look at lithium, for example. Lithium's got three electrons. Excuse me, let me back up. It's got three electrons and three protons. Okay, going around the nucleus, as you know, would be the three electrons. Did you cover any of this in 305? A little bit. Did you talk about London dispersion forces? Okay, so you all know what they are. Okay, London dispersion forces simply are unequal arrangement of the electrons. Because we have vectors here now. And those vectors at 1 nanosecond in time are perfectly balanced and cancel each other out. The rest of the time, the vectors don't cancel. So that's a rare event when they perfectly balance. And it's a very common event that they don't. So when you get a lopsided set of electrons, something like that, you've got more polarity on the left side than the right side. Hence, you have a polar molecule. Now, these London dispersion forces are very weak, very, very weak. But all molecules, No exceptions have London dispersion forces. So okay, we have ethanol. This would be 2-carbon alcohol. And let's say we have one, 3 propane diol. And I said, list the intermolecular forces for these two molecules, then predict which one has a higher boiling point, surface tension, and melting point. So what you do is right off the bat, you'd say LDF, because all molecules have LDF. Okay, what else does this have? Well, it has a CO bond right here. And as we went up here, the CO bond has got 1.0, so it's definitely polar. And that would be classed as a dipole intermolecular force. Sometimes they're called permanent dipoles, as opposed to the transitory dipoles in London dispersion forces. Okay, it also has a hydrogen bond. And doing the same analysis over here, we have 2 CO and we have 2 hydrogen bonds. So intermolecular force-wise, are these molecules equivalent? No, definitely not. The 3-carbon diol has many more very, very polar, strong dipoles in it. These hydrogen bonds really outweigh. So which one has a higher boiling point? Left or right? Which ones have more polar dipoles in it? This guy here. This is twice as much as that one. Hence, this has twice the polarity of ethanol. Hence, its boiling point is higher. Its melting point is higher. Surface tension is higher. Okay. I hope that dovetailed with your 305 intermolecular forces. Now, if you were a bug, say you were a mosquito, and there was a puddle of ethanol and a puddle of the diol, which would be easier to land on? Left or right? That'd be one of them. The one with the higher intermolecular forces. One way they kill mosquitoes in Florida in the late 50s, early 60s, when I was there with my dad, he was in the Air Force. We were stationed at Homestead Air Force Base. The base told us to pour gasoline on all puddles in our backyard, because gasoline is mostly made up of octane, So its intermolecular forces are very, very low. So when a mosquito lands on the puddle of the gasoline on it, the surface tension isn't enough, so they drop down and don't do so well. Can't lay their eggs, nothing. It was a horrible idea, but it worked, along with spraying the neighborhood with DDT. That was another thing they did in the 50s and 60s. Okay, so that's concludes Unit 1 content. Okay, every single test is going to have intermolecular force questions. Every test is going to have reactions. Every test is going to have naming. And possibly some other stuff, but those for sure, those will be on there. Okay, so what I'm going to do is end this video, and I'm going to start